you can see here that each one of these elementary matrices does a row operation. D times A gives me multiplying the second row by 5, and that's because matrix D is the identity matrix with the second row multiplied by 5, right? Or if we look at matrix B, right, what does that do? That's the identity matrix, but we added the third row to the first row. Do you guys see that? So if I do B times A, it will add the third row to the first row, and that's why 1 plus 7 is 8, 2 plus 8 is 10, 9 plus 3 is 12. Did any of you guys come up with what we want for matrix F to be? There you go. Good. 0, 0, 1, 0, 1, 0, 1, 0, 0. If you look at that matrix, that's the identity matrix where what did you do to it? Switch rows 1 and 3. So if I take that and apply it, in other words, multiply it to A, it switches rows 1 and 3. Question, Anthony?
Wherever you do the identity, then once you multiply the identity that you change, you can do it.
It'll do that to the following matrix, yes, which is really nice. Very powerful. What it kind of shows you is how multiplying by the inverse works. Actually, it shows you how to compute an inverse. I mean, in the book, they talk about this. They say, okay, if you want to compute an inverse, what do? And actually, we do this in my finite math class. We'll say, okay, give me a matrix and let's compute the inverse, right? So I'll say, okay, matrix M is 1, 2, 3, 4. And what I do is I augment it in this form with the identity matrix. And then I do the row operations until I get to here. And what'll show up there is the inverse. And you might say, well, why is that? Well, what would be the first thing you would do, by the way, if you were going to take this matrix and start to RREF it? Well, let's see. It would be 1, 2, 3, 4, 1, 0, 0, 1. What's the very first move you guys would do? Yes, yes. So let's say I do something like, negative 3 row 1 plus row 2 is the new row 2. And so what do I get? Well, I get the first row stays the same. The next row would be, let's see, 0. That was the reason you did it. And then this becomes negative 6 plus 4 is negative 2. Negative 3 plus 0 is negative 3, and that's a 1. Right? What's the next step you would do? Well, again, let's leave the first row the same for now. What's the second thing we're going to do? Multiply that second row by? Good. Negative 1/2 times row 2 will be the new row 2. And so you get 0, you get 1, you get positive 3/2, and you get negative 1/2. Right? And now what's the last thing we would do? Now we would use this as my pivot. And so we would do negative 2 row 2 plus row 1 becomes the new row 1. Okay. And so what happens is we get, well, the bottom row is already what it is. It's the top row that changes, right? Now what's negative 2 times 0? Good thing. Because when I add it, I don't want to change that. I want to leave that. I'm trying to get the identity on the left-hand side. Right? Negative 2 times 1 is negative 2. Good thing. Negative 2 times this would be negative 3. plus the 1 is negative 2, if I did that right. And then negative 2 times this is positive 1, so that's that. So supposedly then, M inverse is right here. Here, let me check that very quickly on MATLAB. M is going to be the matrix 1, 2, 3, 4. And let me just find, here's another way to do it on MATLAB. You can type INV of M, or you can type M caret negative 1. It knows that means inverse. That's what we got, right? 3 halves, negative 1 half in the bottom, negative 2 and 1 in the top. And you could check it by doing this. You could say, hey, take that answer and multiply it by M, and we got the identity. Okay. So these are good. Well, the point is, why does this magic algorithm work? Because what you're really doing when you say, hey, how do we get the inverse? You're doing this, guys. You're saying, well, I have M. I do some row operation to it. That was my first move. I'll call E1 the matrix, the elementary matrix that does that row operation. And then I'll do E2 to it, and that means now I multiply it by another elementary matrix. And then I do E3 to it, and now I multiply it by another elementary matrix. Right? So that's what I do. So then the question is, how do you get the inverse? Well, the point is that when we do all this, we get the identity. Right? So the question is, what does M inverse equal? Well, you could see, right, M inverse is equal to E3, E2, E1. Right? So it must be that if on this side, E3, E2, E1, because you're kind of doing it to both sides, right? And so it's going to work. But maybe what's even more important is understanding the order. Well, maybe that does it. Maybe that does it. Here, I want to go through a couple of concepts. But maybe we should finish with the last problem and then go to it. Did you guys try this? What's that? Oh, we didn't get to it? Well, let me do it now then. Okay. So the question is, can you solve this by computing A inverse? So remember, this is of the form A times a vector X equals a vector B. Right? So kind of like I did before, I guess what I could do is I could say, let me let B equal, what is it, 1, 2, 3? And so the question is, can you just say, if I do that, can I solve it by doing this? X is equal to A inverse B. Is that possible? Well, let me try it. I'll come here and I'll say inverse of A times B. Whoa. Warning. This might be wrong, is what it's really telling you. It gave me an answer of 0, 4, 0. But I'm going to tell you right now, that's not right. Because look at the first equation in the group work. Here, look. If you said 0, 4, 0, is it really true that 4 times 2 is 1? No. 4 times 5 is not 2. We had a serious difficulty here. What's the difficulty? Well, the difficulty is this. Matrix A, What does that mean? Oh, it even says results may be inaccurate. What does it say the inverse is? Do you see that top number? 1e plus 16. Do you know what that means? That means 1 times 10 to the 16th. So 1 quadrillion times these numbers. Almost infinity, right? You see, the problem is, guys, let me do this for you. You know what det of A gives you? This matrix has a determinant 0, which means that it doesn't have what? An inverse. What I think is interesting is to do this. Let me make a matrix out of A, and let me put the 3 by 3 identity next to it. Right? And so if I wanted to compute the inverse, the algorithm is to do the reduced row echelon form of that, right? Let's see what we get. Oh, too bad that it's not a nice matrix. Well, actually it is. Over here they store all your matrices that you have. And so this one here called ANS is what it is. Let me just double click it and open it. There it is. So look what it did, guys. 1, 0, 0, 0, 1, 0, negative 1, 2, 0. You see that? It couldn't do it. The problem is that the columns of my favorite matrix are not linearly independent, which means a unique solution when you set it equal to 0, 0, 0. They're linearly dependent. You with me? And so your book gave us the first version of probably like their favorite theorem. And here it is. We'll talk more about this stuff next time because we're down to our last minute here. But here it was. See, it says version 1. The fundamental theorem of invertible matrices. Do you guys know what the word invertible means? Yeah, able to take the inverse, right? Okay. They say A is invertible is equivalent to lots of things. Okay? But look at C. AX equals 0 has only the trivial solution. Well, we know that because of what we did, that's not true, right? We're in a linearly dependent situation, and so we know that matrix A is not invertible. Okay, and they'll add more to this as we go along. Nice work today, guys. I hope you guys learned some stuff. I know you have a lot of homework coming up, but I appreciate the effort you're making.